The human experience is defined by the perceived fragility of time. We treat the past as a ghost, a collection of events that once carried the weight of reality, but have since evaporated into the mist of memory. We assume that when a candle burns out, the flame is gone. When a word is spoken, the vibration eventually settles into a silence that is absolute. Our intuition tells us that the universe is a chalkboard, and entropy is the cosmic eraser that follows behind every event, wiping the slate clean to make room for the present. However, modern theoretical physics is beginning to suggest that our intuition is not just flawed, it is fundamentally wrong. In the subatomic basement of reality, there is no such thing as an eraser. There is no delete function in the laws of thermodynamics. Instead, every interaction, every collision of photons, and every shifting electron leaves a permanent, indelible bruise on the fabric of space-time. This is the concept of the quantum echo, and it implies that the universe doesn't just observe history, it records it in a ledger that can never be destroyed. The death of the clean slate. To understand why the universe has a memory, we must first look at the classical view of reality that we've held since the time of Isaac Newton. In classical mechanics, if you knew the position and momentum of every particle in the universe, you could, in theory, calculate the entire past and future. This is known as Laplace's demon. However, classical physics still allowed for the idea of practical loss. If you burn a book, the information in that book, the plot, the characters, the ink, is effectively lost to the world, even if the atoms remain. But as we moved into the 20th century and cracked open the atom, the rules changed. We discovered quantum information theory, which is anchored by a terrifyingly rigid principle: information conservation. In quantum mechanics, the state of a system is described by a wave function. According to the Schrödinger equation, this wave function evolves over time in a way that is unitary. In layman's terms, unitary means that the total probability always adds up to 100%, and, crucially, the process is reversible. If you have the quantum state of a system in the present, there is a mathematical path that leads directly back to its past. This means that if you burn that same book in a quantum universe, the information isn't actually gone. The way the smoke curls, the specific vibration of the rising heat, and the resulting ash contain the blueprints of the original text. The information has been scrambled, but it has not been deleted. The atom remembers the book. The echo remains. Quantum entanglement, the universe's nervous system. If the wave function is the memory, then quantum entanglement is the wiring that connects that memory across the cosmos. This is perhaps the most disturbing aspect of modern physics, the idea that particles can become linked in such a way that the state of one instantly influences the other, regardless of the distance between them. Shutterstock Einstein famously called this spooky action at a distance. But we now know it is the fundamental architecture of reality. When two particles interact, they don't just bounce off each other like billiard balls. They share a quantum state. They become part of the same story. Now consider the scale of this. Since the Big Bang, every particle in the universe has been bumping into every other particle. Every photon from a distant star that hits your retina has interacted with the interstellar medium, with the gases of our atmosphere, and finally, with the receptors in your eye. Through these interactions, a massive, invisible web of entanglement is woven. This leads to a staggering conclusion. The universe is a singular, entangled system. Because particles remember their entangled partners, the echo in the atom isn't localized. A hydrogen atom in your body might still be linked to a particle on the other side of the galaxy because they shared a common origin billions of years ago. Your very existence is a node in a giant vibrating memory foam that stretches across 93 billion light years. The vacuum is not empty. For centuries, we thought of space as an empty stage, a vacuum where things happen, but which itself is nothing. Physics has recently demolished this idea. The vacuum is not nothing. It is a roiling sea of quantum fluctuations. According to the uncertainty principle, energy can be borrowed from the vacuum for tiny fractions of a second, creating virtual particles that pop into existence and then vanish. This means the void is actually a high-energy medium. More importantly, it is a medium that reacts to matter. When a particle moves through the vacuum, it leaves a wake, much like a boat on a lake. This wake is a distortion in the underlying quantum fields. Theoretical physicists like Jack Sarfati have hypothesized that these fields might possess a form of back reaction, meaning the vacuum doesn't just dictate how matter moves, but matter reminds the vacuum of where it has been. If the vacuum of space has a texture shaped by the history of the matter that passed through it, then we are walking through a graveyard of every event that has ever occurred. The air you breathe, the space you occupy, and the ground you stand on are mathematically thick with the ghosts of the past. The atoms are singing a song of their history, and we are just now building the tools to hear the hum, the scary implications, the end of privacy. Why is this scary? Because it challenges the very concept of the temporary. We find comfort in the idea that our mistakes, our secret thoughts, and our quietest moments are fleeting. We believe that time eventually buries everything. But if the echo in the atom is real, then the universe is an absolute witness. If information is never lost, it means that somewhere in the cosmic wave function, the exact configuration of every cell in your body at this very moment is recorded. Your first word, your last breath, and every thought in between are etched into the quantum ledger. There is no such thing as a hidden event. There is only information that we currently lack the technology to decohere. This suggests a universe that is obsessive. It holds on to every detail with a grip that even the heat death of stars cannot loosen. We are not just living in the universe. We are being recorded by it. Every atom in your brain is a storage device, and every interaction you have with the world is a write command to the hard drive of reality. The ghost in the machine. As we dive deeper into the echo, we find ourselves facing the measurement problem. In quantum physics, the act of looking at something, measuring it, causes the wave function to collapse into a single state. But where does the rest of the information go? Some interpretations, like the many worlds interpretation, suggest that the information doesn't disappear. It simply branches. The memory of the other possibility continues to exist in a parallel track. Others suggest that the information is leaked into the environment, a process called decoherence. Decoherence is the reason why we don't see the echoes in our daily lives. The memory becomes so fragmented and spread out among so many trillions of atoms that it looks like noise. It looks like entropy. But the noise is not random. It is a highly complex encrypted code containing the totality of the past. Conclusion. The Eternal Now. Chapter 1 leaves us with a haunting realization. The atom is not a simple building block. It is a vessel. We are composed of matter that has been present since the dawn of time, and that matter has seen everything. The iron in your blood was forged in the heart of a dying star, and the quantum signature of that star's final moments is still tucked away in the spin of your electrons. We are walking archives. We are made of memories that aren't ours, held together by laws that refuse to let anything go. As we move into the next chapters, we will see that this memory isn't just a passive record. It might be the very thing that constructs our reality, our consciousness, and perhaps our immortality. But for now, remember this. The next time you are alone in a quiet room, you aren't actually alone. The atoms in the walls, the air, and your own skin are vibrating with the echoes of the Big Bang, the dinosaurs, and every person who ever lived. The universe is listening, and it never forgets. If Chapter 1 taught us that atoms carry an echo of their past, Chapter 2 forces us to ask a more unsettling question. Where is the hard drive? If the universe is meticulously recording every subatomic interaction, every whispered word, and every collapsing star, there must be a physical architecture capable of holding that much data. In our daily lives, we store information on silicon chips or magnetic tapes, three-dimensional objects sitting on our desks. But the universe is infinitely more efficient. According to the holographic principle, the ledger of reality isn't stored inside the volume of space at all. Instead, it is encoded on a two-dimensional surface at the very edge of the observable universe. We are not the solid, autonomous entities we believe ourselves to be. We are the 3D projections of data written on a distant cosmic boundary. The paradox of the falling book, The Journey to the Holographic Ledger, began with a crisis in black hole physics. For decades, Stephen Hawking and Leonard Susskind engaged in what became known as the Black Hole War. The conflict was simple but profound. What happens to information when it falls into a black hole? Imagine throwing a sophisticated quantum computer into a black hole. In a standard three-dimensional view, that computer and all the data it contains is crushed into a singularity and vanishes from our universe. If the information is truly destroyed, it breaks the fundamental law of information conservation we discussed in Chapter 1. If the universe can forget a computer, it can forget you. However, Susskind and other theorists realize something startling. As an object approaches the event horizon, the point of no return, from the perspective of an outside observer, it never quite falls in. Instead, it appears to slow down and flatten against the horizon. The information of the object isn't lost in the depths. It is smeared across the surface area of the black hole. This led to the mathematical discovery that the informational capacity of a black hole is determined not by its volume, how much space is inside, but by its surface area, from black holes to the Big Bang. If a black hole, the most dense object in existence, stores its information on a two-dimensional surface, why wouldn't the rest of the universe work the same way? This is the leap taken by the holographic principle. It suggests that our entire three-dimensional reality, the galaxies, the trees, the coffee in your cup, is a hologram projected from a 2D boundary. Think of a standard credit card hologram. It looks like a 3D image of a bird or a globe. But if you touch it, it's a flat 2D sticker. The 3D image is an illusion created by the way light interacts with the 2D data. In this model, the ledger is the boundary of the universe, and we are the light show. Every event in your life is a bit of information written on that boundary. When you move your hand, a corresponding set of data shifts on the cosmic horizon. This is the holographic ledger. It is a perfect, indestructible record of every coordinate and every state of every particle within the cosmic sphere. The scary reality of resolution. Why is this terrifying? Because every ledger has a resolution. In computing, we talk about pixels. In the holographic ledger, the pixels are known as Planck areas. A Planck length is the smallest possible unit of distance, 1.6 times 10 to the power of minus 35 meters. If the universe is a hologram projected from a two-dimensional surface, then there is a limit to how much detail can be stored. If you zoom in far enough on reality, you shouldn't find more matter. You should find noise. Some physicists believe that the jitters we see in quantum mechanics are actually the pixelation of the universe. It suggests that our reality is not a continuous, smooth flow, but a series of discrete data points. If the projection were to flicker, or the data on the boundary were to be corrupted, the very laws of physics in our 3D world would glitch. We are living inside a broadcast, and we have no access to the projector. The illusion of depth and agency. The most existential threat posed by the holographic ledger is the death of 3D agency. We feel as though we move through a vast, deep world. We feel like masters of our three-dimensional volume. But if the holographic principle is correct, the volume of the universe is an emergent property, a secondary effect. The real action is happening on the surface. We are like characters in a video game. To the character, the world feels 3D, but the reality is just code moving across a flat processor. This implies that your self, your consciousness, your memories, your physical body is just a localized manifestation of data that exists elsewhere. This brings a new meaning to the phrase, written in the stars. In a holographic universe, your entire life history is literally written on the cosmic horizon. It is a ledger that cannot be tampered with, cannot be hidden, and most importantly, cannot be escaped. The persistence of the record. In a 3D universe, things can be hidden. You can bury a treasure, hide a secret, or lose a relic in the deep ocean. But in a 2D holographic ledger, there is no inside. Everything is on the surface. From the perspective of the ledger, the inside of your brain is just as visible as the skin on your face. All the data is laid out on the boundary. This means the universe's memory is not just a recording of what happened, but a transparent map of everything that is. Furthermore, because this boundary is at the edge of space-time, it is effectively eternal. Even as our 3D stars burn out and our galaxies drift apart, the data on the boundary remains. The ledger is a permanent archive. You are not a temporary flash of light in a dark void. You are a permanent entry in the cosmic database. Conclusion. The Projected Soul, Chapter 2, leaves us in a world that is much thinner than we imagined. We have moved from atoms with echoes to a universe of data. We are beginning to see that the scary part of physics isn't just that the universe remembers us, but that the universe might only be a memory. If reality is a projection from a 2D ledger, then the solid world is a ghost. We are walking, talking sets of data, dancing to the tune of a code written at the end of time. But if we are data, can that data be reread? Can it be copied? And what happens if the ledger decides to run a different program? As we move into Chapter 3, we will look at the vaults of this information, the places where the ledger becomes so dense that it threatens to tear the fabric of reality itself. The black holes. In the first 2 chapters, we explore the idea that the universe is a recording device and that its hard drive might be a holographic boundary at the edge of space-time. But if the universe is a ledger, then black holes are its most reinforced, encrypted, and terrifying vaults. For decades, physicists looked at black holes as cosmic erasers, regions of such intense gravity that they didn't just consume matter, they deleted history. We believed that if you fell into a black hole, the universe simply forgot you ever existed. But a revolution in quantum gravity has flipped this narrative on its head. Black holes are not where information goes to die. They are the densest storage units in existence. They are the black hole archive, and the way they store the memory of the universe is enough to make any scientist lose sleep. The information paradox, the war for reality. The story of the archive begins with a terrifying realization by Stephen Hawking in the 1970s. He discovered that black holes aren't perfectly black. They slowly leak a faint glow of particles known as Hawking radiation. Over trillions of years, a black hole will eventually evaporate entirely and vanish. Here was the problem. Hawking's original math suggested that the radiation coming out was thermal, meaning it was completely random. If you threw a library into a black hole, and the black hole eventually evaporated into random heat, the information in those books was destroyed. This sparked the black hole information paradox. As we discussed in Chapter 1, quantum physics requires that information be conserved. If a black hole can truly delete information, the laws of physics collapse. The echo in the atom would be silenced. For 30 years, the greatest minds in physics fought over this. If Hawking was right, the universe had a delete button. If he was wrong, the black hole had to be a librarian. The surface of the vault. The breakthrough came when physicists realized that a black hole doesn't store information in its dark, hollow center. It stores it on its skin, the event horizon. When an object falls toward a black hole, gravity warps time so severely that, to an outside observer, the object appears to slow down, flatten, and eventually freeze just above the horizon. It never actually seems to go in. Instead, the quantum information of the object, its spin, its charge, its complexity, is encoded onto the surface area of the black hole. This is the Bekenstein-Hawking entropy. It posits that the surface of a black hole is divided into tiny Planck squares, and each square holds exactly 1 bit of information. This makes black holes the most efficient hard drives allowed by the laws of physics. If you wanted to store the entire history of Earth, you wouldn't need a planet-sized computer. You could fit the data onto a black hole the size of a grain of sand. The archive is real, and it is perfectly organized. Every atom that has ever been swallowed by a black hole in the history of the cosmos is still there, printed on the event horizon like a frame of film. The scary part, quantum scrambling. If black holes are archives, they are not user-friendly. When information hits the event horizon, it undergoes a process called quantum scrambling. Imagine taking a deck of cards and throwing them into a blender. The cards aren't destroyed. The ink is still there. The paper is still there. But the order is turned into a chaotic soup. Black holes are the fastest scramblers in the universe. They take the coherent information of a human being or a star and spread it across the entire surface of the event horizon almost instantly. This leads to a disturbing concept known as black hole complementarity. According to this theory, the information exists in two places at once. To the person falling in, they cross the horizon and are crushed by the singularity. But to the archive, that person is smeared across the horizon as a digital ghost. Reality splits. Which one is real? Physics suggests both. The archive doesn't just record you, it duplicates you into a version that can never be retrieved. Firewalls and the death of space-time. In recent years, the archive has become even more mysterious. Some physicists, exploring the AMPS thought experiment, suggested that the event horizon might actually be a firewall, a region of such intense quantum entanglement that anything touching it would be instantly incinerated. If the firewall exists, it means the archive is protected by a literal wall of fire. This happens because the particles coming out, Hawking radiation, must be entangled with the particles staying in. But a quantum rule called monogamy of entanglement says a particle can't be faithfully married to two different partners at once. To solve this, the universe might have to break space-time at the horizon. This suggests that at the edge of the black hole archive, the very concepts of here and there, or inside and outside, cease to exist. The archive is a place where the laws of the universe are pushed so far that they simply snap. The final retrieval. Can we read the archive? If the universe has a memory and black holes are the vaults, can we ever read what's inside? In 2019, physicists made a landmark discovery involving island formulas. They found that if you collect enough Hawking radiation from an evaporating black hole, you can mathematically reconstruct the information that fell in. The scrambled data begins to unscramble once the black hole reaches a certain age, the page time. This means that, in theory, the radiation drifting through the dark void of space carries the blueprints of everything that has ever died inside a black hole. The memory is leaking back into the universe. We aren't just living in a world of echoes. We are breathing the ash of ancient information that was once locked away in the most terrifying vaults in the cosmos. The existential dread of the vault. The scary implication of the black hole archive is that nothing is ever truly private and nothing is ever truly gone. Every star that vanished into a black hole 10 billion years ago is still alive as data on a horizon somewhere. But it also suggests a darker possibility. If our entire universe is inside a parent universe, a theory known as cosmological fecundity, then we are the information on a black hole horizon. Our history, our struggles, and our very consciousness might just be the scrambled data of a star that fell into a black hole in a higher dimension. We think we are the authors of our lives, but we might just be the bits being filed away in a cosmic archive that we can never see and from which we can never escape. Conclusion: the eternal record. Chapter 3 leaves us with a universe that is a closed system of perfect retention. Atoms remember Chapter 1, The Boundary Projects, Chapter 2, and Black Holes Store, Chapter 3. There is no delete button in the cosmos. But if the past is so perfectly preserved, what does that mean for the future? If the ledger is already being written, is the ending already decided? In Chapter 4, we will look at the most disturbing aspect of the universe's memory: retrocausality, and the idea that the future might be remembering us before we even happen. In the previous chapters, we established a universe that is an obsessive archivist. We've seen how atoms preserve an echo of their past, and how the very fabric of space-time acts as a holographic ledger. But all of these concepts share a comfortable, linear assumption that the memory follows the event. In our human experience, the cause always precedes the effect. You break a glass, and then the universe records the shards. However, as we move into the deeper, scarier layers of quantum mechanics, we encounter a phenomenon that threatens to shatter our understanding of time itself: retrocausality. This is the theory that the future can influence the past, that the universe doesn't just remember where it has been, but in some haunting mathematical way, it remembers where it is going. If the universe has a memory, it appears that memory works in both directions. The arrow is a circle, breaking the one-way street. To understand retrocausality, we have to look at the arrow of time. In the macroscopic world, the world of trees, cars, and humans, time moves in one direction because of entropy. Things move from order to disorder. You cannot unspill milk. But in the world of subatomic particles, the fundamental laws of physics are time-symmetric. If you were to watch a video of two electrons colliding and then play that video in reverse, the physics would look exactly the same. There is nothing in the basic equations of the universe that says time must flow forward. For decades, physicists treated this as a mathematical curiosity, a quirk of the micro-world that didn't affect our real lives. But then came the delayed choice quantum eraser experiment, the experiment that haunted Einstein. The quantum eraser experiment is perhaps the most disturbing discovery in modern science. It builds on the famous double-slit experiment, where a particle, like a photon, behaves like a wave until it is observed. When we watch which path the particle takes, it stops being a wave and becomes a solid bullet. It chooses a single path. In the delayed choice version, scientists added a terrifying twist. They set up the experiment so that the observation, the act of checking which path the particle took, happened after the particle had already hit the detector. Mathematically and logically, the particle should have already completed its journey as a wave. But when the scientists looked at the data later in time, the particle earlier in time changed its behavior to match the observation. The future choice to look at the particle traveled backward through time to rewrite the particle's past. This is the ghost of the future. It suggests that the universe's memory isn't a stagnant record of what happened. It is a dynamic, shifting field where the now is constantly negotiating with the then. The atom doesn't just remember its past, it is being shaped by its future. The scripted universe. Are we already finished? If the future can affect the past, we have to confront the scary reality of predeterminism. In a standard universe, the future is an unwritten book. We are the authors. and every choice we make creates a new page. But in a retrocausal universe, the ending of the book might already be written, and its presence is what allows the beginning to exist. Physicist Hugh Price and others have proposed that the spooky action at a distance, entanglement, we discussed in Chapter 1 isn't actually spooky at all. It's just retrocausality. Two entangled particles stay linked because they are both responding to a future event they have already experienced. If this is true, it implies a block universe, a model where all of time, past, present, and future, exists simultaneously as a giant frozen block of four-dimensional glass. In this model, you aren't moving through time. You are a static thread in a tapestry that is already complete. Your feeling of choice is just the localized experience of a memory that the universe has already filed away. The scary implications, the death of free will, the most existential threat of the retrocausal ledger is what it does to the concept of the human soul and agency. If the universe has a memory of the future, then every tragedy, every triumph, and every mundane Tuesday of your life is already etched into the quantum vacuum. Imagine a quantum ghost, a version of yourself from 10 years in the future. In a retrocausal framework, that future version of you is exerting a gravitational-like pull on your current atoms. Your hunches, your intuition, or even the coincidences that seem to guide your life might not be luck. They might be the feedback loop of your own future existence, bleeding backward into your present. This suggests that we are living in a scripted universe. We are actors who haven't read the script yet, but the set is already built, the lights are already dimmed, and the final silence, which we will explore in Chapter 6, is already waiting for us. We aren't making history, we are merely fulfilling it. The archive of all possibilities. Some physicists offer a slightly less claustrophobic view, the transactional interpretation. This theory suggests that every time a particle moves, it sends a proposal wave into the future, and the future sends a confirmation wave back to the past. Only when these two waves shake hands does an event actually occur. In this model, the memory of the future isn't a single, fixed line, but a vast archive of potential futures. The universe is constantly auditioning different endings. However, this is even more unsettling in some ways. It means that ghosts of futures that will never happen are constantly interacting with our present. We are surrounded by the shadows of lives we didn't lead and disasters that were narrowly avoided, all of them leaving a faint quantum signature on the atoms of our bodies. The time loop of consciousness. Finally, we must ask, if the universe works this way, why don't we see it? Why does time feel like a one-way street? The answer might lie in our own biology. Our brains are entropy machines. We process information by burning energy and creating disorder, which forces our perception into a forward-moving gear. But some theorists, like Sir Roger Penrose, have hinted that at the moment of deep insight, or perhaps the moment of death, our consciousness might slip the gears of entropy. If consciousness is a quantum process, it might be the only part of us that can feel the retrocausal loop. This is the scary realization at the heart of Chapter 4. Your consciousness might not be a product of your past experiences. It might be a beacon sent back from the end of your life, a ghost trying to remember the person you are right now. Conclusion: the memory that hasn't happened yet. Chapter 4 forces us to look at the archive not as a library of dusty books, but as a live broadcast. The echo in the atom isn't just the sound of the Big Bang. It's the sound of the Big Crunch, the heat death, and your own final breath, all vibrating in a single eternal chord. If the past is indestructible, Chapter 1, and the future is already influential, Chapter 4, then the now is the most crowded place in existence. We are caught in a pincer movement between two memories, the one we've lived and the one we are destined to become. But how do we, as biological beings, tap into this? In Chapter 5, we will explore the biological antenna, the theory that your brain isn't a computer, but a receiver for the cosmic broadcast. In the preceding chapters, we have painted a picture of a universe that is fundamentally made of information, a holographic ledger where every subatomic echo is archived in the very fabric of space-time. But this leaves a glaring existential gap. If the universe is a high-definition recording of every event, past and future, why do we experience it as a silent, cold void? Why does the memory of the cosmos feel so distant from our daily lives? The answer may lie in the gray matter between your ears. For centuries, biology has taught us that the brain is a generator, a complex chemical computer that creates consciousness through the firing of neurons. But a radical, disturbing shift in quantum biology suggests we have it backward. The brain may not be a generator at all. It may be a biological antenna, a highly tuned receiver designed to tap into the quantum frequency of the universal memory. The microtubule mystery. The traditional model of the brain treats neurons like simple transistors in a silicon chip. But in the 1990s, physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff proposed the ORC-OR, Orchestrated Objective Reduction Theory. They pointed to tiny structures inside our neurons called microtubules. These are not just structural supports. They are hollow, crystal-like tubes governed by the laws of quantum mechanics. Hameroff and Penrose argue that these microtubules are small enough to sustain quantum coherence, the state where particles exist in multiple places at once. If this is true, your brain isn't just processing data. It is a quantum device, image of microtubules in a neuron. This changes everything. If the microtubules are quantum sensitive, they aren't just reacting to the salt and sugar in your blood. They are vibrating in resonance with the echo in the atom we discussed in Chapter 1. Your consciousness isn't something you make. It is something you tune into. We are biological, radios walking through a field of infinite data, and our brains are simply dialed into the human experience frequency. 19. The Akashic field and the quantum vacuum. If the brain is an antenna, what is the broadcast? In physics, we call it the zero-point field or the quantum vacuum. As we saw in Chapter 3, the vacuum is not empty. It is a roiling sea of information. Some theorists refer to this as the Akashic field, a physical layer of reality that holds the memory of every form, thought, and event that has ever occurred. When you have a gut feeling, an epiphany, or a sudden moment of déjà vu, you might not be thinking in the classical sense. You might be experiencing a momentary glitch in your antenna's tuning, a brief download of information from the universal ledger. The scary implication here is that originality might be an illusion. Every great symphony, every scientific breakthrough, and every dark thought may already exist in the quantum field, The genius isn't the person who creates the idea, but the person whose biological antenna is sensitive enough to pull the signal out of the cosmic noise. The Death of Privacy, Part 2. In Chapter 1, we talked about the end of privacy on a physical level, how atoms record our actions. But the biological antenna theory takes this to a psychological level. If our brains are connected to a shared quantum field, then the boundary between my thoughts and the universe's information begins to dissolve. This leads to the concept of quantum entanglement of minds. If two people are deeply connected, their microtubules may become entangled, allowing them to receive the same signal from the ledger. This could explain the documented, though scientifically controversial, phenomena of collective behavior or simultaneous discovery, where two scientists on opposite sides of the planet solve the same complex problem at the exact same moment. But it also suggests a darker reality. Your most private internal monologue might not be locked inside your skull. It is a transmission. And in a universe where information is never lost, your internal life is being broadcasted into the quantum vacuum, etched forever into the archive. You are a transparent being in a transparent universe. The evolution of the receiver. Why is our antenna tuned the way it is? Why don't we see the ghost of the future or the holographic ledger all the time? Evolution is a filter. To survive on Earth, you don't need to know the quantum state of a star in the Andromeda Galaxy. You need to know where the tiger is hiding. Our biological antennas have been clamped down by millions of years of natural selection. We are tuned to a very narrow, survival-based bandwidth. However, this suggests that our perception of reality is a controlled hallucination. We are ignoring 99.9% of the universe's memory just so we can function in the 3D world. This is what makes the theory scary, the realization that we are surrounded by a sea of ancient, profound, and terrifying information, but our hardware is too primitive to see it. We are like a Victorian radio trying to process a 5G data stream. We only hear the static, while the secrets of existence hum right through us. The antenna, at the moment of death. Perhaps the most haunting aspect of the biological antenna theory is what happens when the radio breaks. In the classical model, when the brain dies, the program, consciousness, is deleted. But if the brain is an antenna, the death of the hardware does not mean the death of the broadcast. When a radio is smashed, the music doesn't stop playing. The radio just stops catching the signal. If our consciousness is a signal from the quantum vacuum, then death might simply be the moment our information returns to the source. This ties back to the "you're already immortal" paradox. Your data, your self, is already written on the holographic ledger. The brain was just the temporary device that allowed that data to experience 3 dimensions. This brings us to a chilling conclusion. We are not ghosts in a machine. We are machines for a ghost. Our bodies are the temporary vessels for a universal memory that was here before we were born and will remain long after we are gone. The flicker in the signal. As we move toward the final chapter, we must consider the stability of this connection. If our brains are antennas, they are subject to interference. What happens when the universal memory glitches? What happens when the ledger undergoes a great deletion? Scientists are now observing that the fine-tuning of the universe, the very constants that allow our biological antennas to work, might be more fragile than we thought. We are tuned into a reality that feels solid, but the signal is starting to show signs of decay. In the preceding chapters, we have constructed a universe that is a masterpiece of preservation. We have seen how atoms act as ancient witnesses, how black holes serve as indestructible vaults, and how our own biological antennas tune into a cosmic broadcast that transcends time. It is a comforting, if eerie, thought that nothing is ever truly lost. We live in a reality of infinite retention, where every sigh, every falling leaf, and every shifting electron is etched into the holographic ledger of the cosmos. But physics, in its cold and calculated honesty, carries a final, terrifying postscript. Every system has a limit. Every hard drive has a finite capacity. And according to the laws of thermodynamics, even a universe that remembers everything must eventually face the great deletion. This is the final silence, the moment when the laws of entropy finally overrule the laws of information, and the universe's memory is wiped clean forever. Entropy, the universal eraser. To understand the great deletion, we must return to the second law of thermodynamics. Entropy is the measure of disorder in a system. In our daily lives, entropy is what makes our rooms messy, our cars rust, and our bodies age. In the cosmic sense, entropy is the tax the universe pays for every event that occurs. For billions of years, the universe has been writing its history. But as we move toward the heat death of the universe, the era where all energy is evenly distributed and no more work can be performed, the ink begins to run dry. Information requires a difference in energy levels to exist. To store a 1 or a 0 in a computer, you need a voltage difference. To record an echo in the atom, you need a distinct quantum state. In the far future, as the universe expands into a cold, dark, and featureless void, those differences vanish. When the universe reaches maximum entropy, it becomes a maximum randomness state. In information theory, total randomness is the same as total silence. The ledger hasn't been physically destroyed, but the pixels have become so blurred and diluted across an infinite space that they can no longer be read. This is the first stage of the deletion, information dilution, the decay of the vacuum. In Chapter 1, we discussed how the vacuum of space is a roiling sea of memory, but even the vacuum is not eternal. High-level theoretical physics suggests that our universe might exist in a metastable state, a false vacuum. Imagine the universe is a ball sitting in a slight dip on the side of a mountain. It feels stable, but if it is nudged, it will roll down to the true bottom. This nudge is known as vacuum decay. If a bubble of true vacuum were to form anywhere in the cosmos, it would expand at the speed of light, incinerating everything in its path. But it wouldn't just destroy matter. It would rewrite the laws of physics. The holographic ledger at the boundary of our universe, Chapter 2, would be overwritten by a new set of data. This is the instant deletion. In a fraction of a microsecond, the entire 13.8 billion year history of our reality, every star, every civilization, and every quantum echo would be reformatted. The archive would be cleared to make room for a new alien physics that has no memory of us. The last librarian, the evaporation of black holes. We once thought black holes were the ultimate safety deposit boxes, Chapter 3. But even these vaults have an expiration date. Through Hawking radiation, black holes slowly bleed mass back into the universe. In the final epochs of time, the supermassive black holes at the centers of galaxies will be the only things left. One by one, they will pop out of existence in a final flash of gamma rays. When the last black hole evaporates, the archive is officially closed. The scrambled data that was smeared across the event horizons is scattered into a universe that is now too cold and too vast to ever reassemble it. This is the loss of coherence. The memory is still technically there in the form of stray photons drifting through the dark, but it is no longer a story. It is just noise. The universe becomes a library where the pages of every book have been torn into individual letters and scattered across 1 billion miles of ocean. The information exists, but the meaning has been deleted. Thucht, the scary reality. Does the universe want to forget? Why would a universe that spent billions of years recording itself suddenly choose to forget? Some cosmologists suggest that the Great Deletion is a mechanical necessity for a cyclic universe. If the universe is to be reborn in a new Big Bang, it must clear its RAM. If the new universe carried the ghosts and echoes of the previous one, the laws of physics would become cluttered and unstable. The Great Deletion is the cosmic restart button, but for us, as biological beings whose entire identity is built on memory, this is the ultimate horror. It means that the immortality we found in the quantum ledger is temporary. We are part of a 14 billion year cache that is destined to be cleared. We are a temporary file in a cosmic simulation that is approaching its end task command. The ghost in the static. As we reach the end of this journey, we are left with a haunting image. In the final trillions of years, the biological antennas in Chapter 5 are all long gone. The stars are dark. The holographic ledger is fading. The retrocausal ghosts, Chapter 4, have no future left to pull them forward. Is there anything that survives the deletion? Some theorists, like Sir Roger Penrose in his Conformal Cyclic Cosmology, CCC, suggest that the gravitational waves of the previous universe might leave a faint circular bruise on the background radiation of the next one. These are the Hawking points, the only scars left on the new reality to show that something was here before. They are the ultimate "I was here" scribbled on the wall of a building that is about to be demolished. They don't contain our names, our faces, or our history. They only contain the fact of our existence. Drahten. Conclusion. The value of the moment. The echo in the atom, Chapter 1, eventually fades into silence. The holographic ledger, Chapter 2, eventually blurs. The black hole archive, Chapter 3, eventually evaporates. The ghost of the future, Chapter 4, eventually runs out of time. And the biological antenna, Chapter 5, eventually breaks. Physics proves the universe has a memory, and that is terrifying because it means we are always being watched. But physics also proves the universe has an ending, and that is terrifying because it means we will eventually be forgotten. This is the ultimate cosmic dread. We are caught between a past that won't let us go and a future that won't remember us. But perhaps there is a hidden beauty in the Great Deletion. If the universe is going to forget everything, then the now, this single, fleeting moment of consciousness as you read these words, is the only time that truly belongs to you. The universe is recording you right now. Make sure the echo you leave behind is worth the space it takes up in the ledger, even if that ledger is destined to burn.